A week ago today, I turned 80. Okay? That means I have a whole new agenda. And the agenda, among other things, is that I go back and do the stuff that I had never had time to do when I was full-time teaching. Okay? And I also don't need my favorite problems anymore. I've saved them for the last 50 years, just so I had a longitudinal test of how people did them. But now I don't have to, so I'm going to write a whole series called My Favorite Problems, and this is the first one. I'm doing it as a project with Tom Cooper, a former student who's here tonight, and you'll see later on how he solved a problem. Well, he solved the wrong problem, which started our collaboration. Okay, okay, so now, try this. People have heard me lecture before know that I got started in the fourth dimension because of comic books, or funny books as we used to call them, and I still get motivation for my student projects out of comics. How many people have seen Foxtrot or read Foxtrot over the years? Bill Ammon chooses some really good mathematical problems as part of his thing. He has a figure character there, Jason, a very obnoxious, well, a very fine, bright, young student. Here he is, typical thing. Would you say this glass is half full or half empty? Half empty, his mother says. Half full, his father says. Half empty, his brother says. Half full, his sister says. And he says, you're all wrong. The glass is 5/12 full and 7/12 empty, you suckers. Now, that's a good problem, because what's the shape of this glass? Okay. If it's a straight up tumbler and you go halfway up, it's half and half. But it's not. You can see the shape is not that. So the question is, what is the ratio of the top to the bottom that would give him the ratio he promises? So let's see if we can do that. What you do, if you give it to the students, is they look in the book and see that the Egyptian problem of how to solve the volume of a cone, of a pyramid, is essentially a two-dimensional problem. You slice across the thing, that sets up a ratio between the R and the S and the heights, the two heights, the complete height and the partial height. So you can do that, and indeed, if you do it, you can solve it. On the other hand, every once in a while, you have a student who solves it for you in a brilliant way. This is the solution. He handed it in. Can you hear it? Well, it was a good solution. It used to be. Well, okay. This is not the good solution. This is the same solution, but in the third dimension. But what I really had in mind, since it was a two-dimensional comic strip, is the two-dimensional problem. And one student who solved it most brilliantly handed this in. Come on. And wrote at the bottom, W-A-L-L-A. I said, what's that? He said, voila. Okay. In any case, it is voila, because you take the midpoint, you divide it up into these triangles. There are 7 on the top, 5 on the bottom. Now, he just guessed it was twice as long. It looked like that. It doesn't work if you have, well, more complicated rational numbers. It certainly doesn't work for irrational slopes or irrational things, but that worked really nicely. And in fact, you have these downward pointing things and these upward pointing things, and they fit together really nicely. Now, as I said, Tom Cooper misunderstood the question. He didn't realize I wanted the two-dimensional problem. He solved the three-dimensional problem, which turns out to be more complicated. It looks more like what I expected to get in a class. This class, by the way, was for juniors and seniors who were preparing to be high school teachers at Georgia, University of Georgia, in the ed school, where I was teaching in math and ed. And Tom was a grad student at the time. He's now a full professor. And we promised at that time that we would use his solution and my solution, or the other solution, to write a paper together. And we're doing it, okay? The first part of it will be what we see today. Now, of course, things have changed since the last time. Things have changed since the last time. Come on. It's not, okay. Because now you can actually go back and do the Egyptian pyramid problem in the same kind of way, where you're bringing pyramids up from the top, bottom, 4 pyramids up to the halfway spot. I started out by a 2x2 on the bottom and a 4x4 at the top. And so we're taking a look at the lower half of the stip. And you notice you've got 4 things coming down, and, come on. Well, I used to be so good at this. Sorry, why don't you just stay up here, okay? I'm sorry. I'm managing to... just pressing the button, yeah? It's like working. So once you get a new solution to a problem that you care about, then you go back and see what that says about the old problem and the old solution. And you try, as we did here, to put spikes up, spikes down, and count the number. And, oh gosh, that's interesting. There are 4 up on the 4x4, or 2x2, and down there are 3x... I really had to stretch to find 13 to get here, but here we are. So we have that number. But there are additional things, and this is the interesting part of that problem. You don't exhaust it by your things down and things up. You've got these other things in the middle where you have a segment at the top, a perpendicular segment down at the bottom, and you want to try to find the volume of the smallest tetrahedron that meets that conditions. Fortunately, that is a standard problem because what you want to do is cut away. And we have people here who assemble puzzles forever and ever, and you can make this out of wood easily to show that was going to give me the right time. How much time do I have left? Come on.
We do need to wrap up. You will need to wrap up. We're out of time. You're out of time. Sorry.
Okay. Here's another cup, 2.5. This is the same thing here. And a student solved my Air France cup problem, round on the top, square on the bottom, by adding rather than subtracting. And of course, that's a standard technique, but it was brilliant here. I can say that the median section of the first thing was this. And naturally, I was going to show a letter from Martin Gardner, which talks about the fact, since other people did that, it's not to me, but it's to somebody else who was at Rhode Island. So he sent him to me. And this was the first of a series of letters where I was sent things saying, Martin Gardner has told me I should write to you because you can answer my questions. So I figured that that's a good way to retire. Okay? And that's the last time I saw Martin Gardner, 1993, 1998. AMS meeting and MAA meeting, and now I'm off to go on to the next stage of my academic life. Thank you very much.